Hi friends, welcome back to Edupedia world. The last lecture we saw about dispersion of white light caused by a prism. Today we'll jump into the further aspects of spectrum, that is the electromagnetic spectrum. We'll see what a electromagnetic spectrum is and what it is composed of. Here we will see that visible light is just a particular segment, a part of the electromagnetic spectrum, which ranges from the radio waves on one end to the gamma rays on the other end. We'll see the different wavelength ranges and the frequency ranges for the electromagnetic spectrum, and we'll close the lecture with some properties which are common throughout the electromagnetic spectrum. So let's start with today's lecture. In our previous discussion, we saw about the details about the visible light, the Newton's experiment which he conducted on visible light using a prism. But the matter of fact is that visible light is just a small section of the whole electromagnetic spectrum that is available there. The electromagnetic spectrum is the range of wavelengths or frequency which is there, and which is the light, the range of frequencies that is emitted by different sources of light. But the only section that is visible to us is the visible light region, which is in this region. So this is basically 0.4 to 0.8 micrometer. This is micrometer, or as we have seen in the previous discussion, 4000 to 8000 angstrom, right? So this is our range of visible light that is perceived by our eye. But apart from that, the electromagnetic spectrum broadly consists of what is shown in this figure. If we start from the high wavelength, long wavelength lights, then what we have in the extreme over here are known as the radio waves. The radio waves are typically around 10 centimeter and longer. So this region is our radio wave, and they continue to be in the range of kilometers. And this is one of the typical range of wavelength that is used for telecommunication. So this is a very important aspect of our day-to-day life. Now, if we go to a bit shorter wavelength, then we encounter what is known as microwave radiations. Now, the range of microwave radiation is 10 to the power minus 1 meter to 10 to the power minus 3 meter. So this is a bit shorter in wavelength than the radio waves, but still much larger than our visible light. So this is our microwave radiations. Beyond the microwave radiation, if we go to further smaller wavelengths, then we encounter what is known as the infrared radiations. Infrared radiation has a huge range. It starts from roughly 10 to the power minus 3 meters. This whole units are in meters. So it starts from roughly 10 to the power minus 3 meter, that is 1 millimeter, and extends till 0.4 micrometer or 4000 angstrom, that is the red end of the visible spectrum. Hence the name infrared, because beyond that we have the red of the visible light. Okay, so after we traverse through the infrared region, we go into the visible region, the small window of wavelengths that we are actually able to perceive via our eyes. Now, beyond the visible light, we have ultraviolet light. The ultraviolet light starts from 8000 angstrom roughly to 10 to the power minus 8 meters. Okay, so this is 100 angstrom. So this is the range of our ultraviolet light. And again the name ultraviolet, since this is beyond the violet of the visible range, it's called ultraviolet. Now we are already in the range of very short wavelength now, and even shorter wavelength is encountered in the X-ray regions. These are the typically from 10 to the power minus 8 meter, that is 10 nanometer, to 10 to the power minus 11 meter or 0.1 angstrom. So that is very short wavelength. And beyond the X-ray, we finally encounter which we term as the gamma rays, which are radiations of extremely short wavelengths shorter than 10 to the power minus 11 meter or 0.1 angstrom, and it goes beyond to the much shorter wavelength. So that is the gamma radiations. Now we have discussed the electromagnetic spectrum, the range of electromagnetic spectrum, the different wavelength ranges here, but there is also another approach to see the electromagnetic spectrum. As I discussed briefly in the previous lecture, that the velocity of a light wavelength is frequency times the wavelength. So from this we can infer that the frequency is speed of light upon the wavelength. Now speed of light is roughly 3 into 10 power 8 meter per second, and the wavelength is lambda, that depends on the actual light which we are observing. So the frequency is another approach to see the electromagnetic spectrum, and from this formula you can observe that the frequency and the wavelength are inversely related. So higher the wavelength, lower the frequency. That is what is mentioned here. So low wavelength, low frequency, long wavelength, or short wavelength, high frequency. Therefore what we can say is that radio waves, being the largest wavelength, has the smallest frequency. And there is another relation. Let me write it down. Energy of a particular wavelength is h times frequency, where h is called as Planck's constant. You need not remember this, but the take home from here is that energy is proportional to the frequency. So higher the frequency, higher is the energy of the wavelength. Therefore radio waves are basically much lower energy wavelengths, and gamma rays are the highest energy wavelength. The visible spectrum lies in between in terms of energy. So the whole electromagnetic spectrum can be thought of in two ways, that while going from this direction, from the left to right, from radio wave to gamma frequency, either the wavelength decreases or the frequency increases, and since frequency is increasing, the energy is also increasing. Okay, so this is roughly the whole electromagnetic spectrum. I have not gone into details about each individual's spectrum component, the radio wave, microwave, but that is what we will do in our next class. We will see some sources of each individual spectrum region. We will see some properties of it, and the advantages, disadvantages, or harms that it can cause, and the utilities that it has. Now all these subsections of the electromagnetic spectrum follows certain rules which does not depend on the frequency or the wavelength. Those things I will mention here as a common property, right? So one thing, the first thing to mention is electromagnetic radiation does not require a medium. To travel. So it can travel through vacuum. Then all electromagnetic radiation in vacuum travel with a speed of 3 into 10 to the power 8 meter per second. Now this speed obviously differs if the medium is changed, but for vacuum this is 3 into 10 to the power 8 meter per second for all of them. Now all these lights show similar reflection and refraction properties. So they follow laws of reflection and refraction, and these waves, though they are named as electromagnetic waves, they originate from they have components of electric field and magnetic field, but they are not deviated by electric and magnetic field. Not deflected by electric and magnetic fields. And finally, these waves, the electromagnetic waves, are what is called as transverse waves. There are two types of waves. One is called longitudinal waves and the other is called transverse waves. Longitudinal wave, an example is sound wave, and transverse wave, an example is light. So you need not go into the details, but you need to know that this is a kind of transverse waves. Okay, so now you have an idea about the general properties of electromagnetic radiation, the wavelength ranges of the electromagnetic radiation, and using this formula you can also find the frequency ranges. I'll just roughly give you an estimate of the different frequency ranges just for the rough idea about it. So the gamma rays is around 3 into 10 to the power 19 hertz. You must be knowing the unit hertz. Hertz is frequency per second. How many frequencies are there per second? So gamma rays has a very high range of frequency. Rather, it is on the higher end of frequency range. Then the ultraviolet is roughly 3 into 10 to the power 16. So ultraviolet lies between, the X-ray lies between 3 into 10 to power 16 hertz to 3 into 10 to power 19 hertz. You can calculate this from here. There might be slight fluctuations. These are rough values which I am mentioning. Then the visible light, I'm not going to mention the exact value, but it's in the order of 10 to the power 14 hertz. Somewhere between like 4 to 8 into 10 to the power 14 hertz. Then when we come to the range of infrared, that is this, we see it is around 3 into 10 to the power 11 hertz. So infrared lies between 3 into 10 to the power 11 hertz to some value in the order of 10 to the power 14 hertz. And finally radio waves is somewhere around 3 into 10 to the power 7 hertz. Okay. Now this might be a bit different depending on the book you are referring to. This you might have to calculate this. Let me see, 3 into 10 to the power 8 upon 3 10 to the power minus 1, that is 3 into 10 power 9 hertz. So but the demarcation is not very abrupt. Somewhere you can find it 3 into 10 power 10 power 9 hertz, somewhere 3 to 10 power 8 hertz or 10 power 7 hertz. So this is basically a continuation. Okay, so now you have a rough estimate and rough idea about the different components, both in wavelength terms and in the frequency term, and some of the basic properties which is followed by all of them. Next class we will focus on the individual components, that is radio, micro, and all of the rest. So till the next class, have a great day. Goodbye.